In this video, I want to talk to you a little bit about how you can read empirical results, statistical tests that you come across in academic political science journal articles. And the first thing that we might want to do when we're trying to measure something quantitatively is to get a sense of what a typical observation would be. And we can start thinking about this by thinking about a really common, simple kind of measurement we might want to take. Let's say we've got a group of people and we want to know what their average height is, or we want to know something about the height of that group of people. And we measure all of them, okay? And we have height in centimeters, say, right? Well, one thing we might want to know is what is the typical person in that room? What's the typical observation? We might want one measure that summarizes that entire room so we can get a sense of what that room's like, a kind of a snapshot. And the most common ways we do that are to use one kind or another of measures of center. And when we're talking about height, the type of measure of center that we're probably using is something called the mean, right? The average. You're familiar with this, right? So we would take everybody's height in centimeters, we would add all those centimeters up, divide by the number of people in the room, and then we'd have the average height in centimeters in the room, right? And this is a very common measure of center. We see this all the time. We see average education level, average amount of support for the president. We see this all over the place. Another common measure that gives us a sense of a typical observation, a slightly different way to think about it, is something called the median. And this can be advantageous when we're dealing with numbers that might be radically skewed by a really low or really high observation. So we think of height. If we've got a room of 30 people, and all of a sudden LeBron James walks into the room, that's going to skew the results significantly upward, right? And so that our average height might go up by 10 centimeters or something like that, maybe even more. And so it's going to make everyone look taller. On the other hand, if we simply ranked everybody from shortest to tallest, and identified who the middle person was in that rank, the 50th percentile, that wouldn't change much when LeBron James walked into the door, in the door, right? That might budge a tiny bit because you've got an additional person, but it's not going to change that much because he's only one additional tall person. And so that is called the median. And so we often rely upon the median for things that might be skewed by really high or really low levels, or really high or really low values. Things like income, for example. We're often not interested in average income. If we had a group of 30 people and Bill Gates walked into the room, our average income would skew quite a bit. What we might want, what might be a better measure of a typical income level in that room would be the 50th percentile, the median in that room. Another measure of center you might run across sometimes is the mode. Here, you're going to use mode typically when you have a bunch of categories. So say you want to know something about people's religions in the United States or something like that. The mode would be the most commonly occurring religion. Oftentimes, the measure of center isn't enough for us. We want some sense of how spread out the different observations are. Is everybody in that room the same height? And therefore everybody's right at average or plus or minus an inch or two? Or do you have a wide range? Do you have some people who are closer to 5 feet and some people who are well over 6 feet? We might want to know that. And so there's different ways that we can represent these measures of spread or measures of dispersion. If we're using a median, one common thing we might see is the range. What's the minimum and the maximum observation, the lowest and the highest observation? We can present other percentiles. One of the most common things we'll see is that you present the middle 50% of the data. What's the 25th percentile to the 75th percentile? And that gives you a sense of the spread around that data. In terms of means, we have different ways to measure measures of spread. One way is the variance. You can think of each observation, each person's height in that room. We take each person's height and subtract it from the mean. So we're going to get some negative numbers, right? There's people who are underneath the mean, and we're going to get some positive numbers, right? If we added all those together, we'd actually get 0. So what we do is we square those numbers. So now they're all positive, okay? And we add them all up. And the smaller number we have means less variance, means that all our observations are more tightly centered around the mean. The bigger number we have means more variance, more spread around the mean. There's also a measure called the standard deviation, which is simply the square root of the variance. Basically, after you add up all those squares, you take a square root of it, and that also is just another way to represent the spread of the data. Now, so far we've just been talking about one concept. We're measuring one concept and we want to get a quick description of what it looks like. But in political science, we're interested in more than that. We're interested in relationships among multiple concepts. And we measure variables that are connected to different concepts, and we want to know how they are related to one another. And so it can be useful when we look at those relationships, those associations, it can be useful to know how strong are those associations. And there are a variety of different measures of association. I'm not going to talk about all, I'm only going to talk about one of them, but typically their values are range from -1 to 1, where 0 represents no relationship, -1 is a perfect negative relationship, and 1 is a perfect positive relationship. And of course, a negative relationship would be that when the value of one goes up, the value of the other goes down. A positive relationship would be the value of one goes up, the other goes up. One that you may run across from time to time is a very widely used measure of association. It's called the correlation coefficient. It's typically represented as R, and it just shows you how closely two variables are connected. So the closer the R value is to either 1 or -1, the more closely they are related to one another, either positively or negatively. The closer the value is to 0, the weaker the relationship is between the two. Now, when we are looking around the world and we're measuring things, we are typically measuring a sample of some kind, and there's going to be error in every measurement we take. And so when we use measures of association, we're usually testing a hypothesis, right? We're testing a hypothesis we have about the strength of that relationship. And we're using that measure of association to see whether the variables that we're looking at are associated in the way we hypothesized and how strong that association is. But we're also going to want some sense of how likely we might be to be wrong. So I need to talk a little bit about hypothesis testing and statistical significance. Now, the way we test hypotheses is actually, it seems kind of backwards at first, but it makes perfect sense within the logic of science. We need to understand that science is not about proving things. Science is about testing things. Proof is for math and logic. We can prove things mathematically. We can prove things logically. We don't prove things scientifically. We test things scientifically. And so what we do in science is we state a hypothesis, and then we gather data, and then we try to test those data to see if the hypothesis is true. Now, what we do when we test the hypothesis is to actually assume that there is no relationship. And this is called the null hypothesis. And so in science, all knowledge is tenable. All knowledge is tenuous. All knowledge could be rejected. Falsifiability is a key aspect, a key attribute of scientific knowledge. And so we are always willing to discard what we think is true if we find that the evidence doesn't bear it out. And so for that reason, we often test our hypotheses, even though we state that the hypothesis is that one variable leads to another, or one variable is positively related to another. We test the hypothesis using the null hypothesis. We test whether, in fact, there is no relationship between the two. And so what we're actually looking for when we test the hypothesis is the likelihood that the null hypothesis is false. Or put another way, what we want to know is what is the likelihood that we are wrong if we think the null hypothesis is false. So somewhat counterintuitively, it's actually beneficial. It's what we're actually hoping is that we reject the null hypothesis. We're hoping that we look at the data and say, no, there does seem to be a relationship here as far as I can tell. Now, in order to do this, we engage in a process of statistical testing. And you can think of a statistical test as asking, what is the probability that a relationship we've observed would occur by chance? Okay, what is the probability that a relationship we've observed would occur by chance? So we've gathered data, we've run, say, a measure of association, and it shows a strong positive relationship between two variables. When we do a statistical test, we're asking, what's the probability that that observed relationship, that strong positive relationship, is just due to chance? And we are always willing to accept some error in rejecting the null hypothesis. And so that amounts to the probability that we're wrong, okay? But we want that probability to be very low. Now, how low depends on a researcher's goals. As I often say when I talk about this, if we're testing the tensile strength of rivets that are going to be used to put together an airplane, we probably want very, 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 very low probability that we're wrong, right? But in social science, we're usually willing to accept a little bit more error. If we test a hypothesis and we cannot reject the null hypothesis, and the statistical evidence shows that there's very low probability that the relationship we've observed occurs by chance, then we say that relationship is statistically significant. And what that means is that we have rejected a null hypothesis with a specific probability of being wrong. Okay? So we have tested two variables. The measures indicate that there's a relationship there. The null hypothesis seems to be rejected because it looks like there's a relationship. And the probability test shows us that there's very little likelihood that we're wrong about a relationship actually existing. That's statistical significance. That probability is quantified with what we call the p-value. And in social science, we're willing to accept a little bit more probability of being wrong than we might be in some other areas. Generally, we want the probability of being wrong to be less than 5% or less than 0.05. So the logic of hypothesis testing, we assume there's no relationship. We test. If there is a relationship, we ask, what's the likelihood that we're wrong about that relationship existing? If the probability comes in very low, meaning there's very little likelihood we're wrong, then what we say is we fail to reject the null hypothesis. We think there is a relationship between those two variables. Now, there are a variety of contexts in which statistical tests might be used. Sometimes you might just see two different groups compared by their averages. And so you would look at two groups. Maybe somebody is testing different study techniques in different classes. And so you compare the mean test scores of one class versus another class, and you do a significance test to see if that differences between them are in fact significant. If the probability that you made an error comes back very low, then you conclude that there does seem to be a difference between those two groups. Ideally, in social science, we are hoping to test causal relationships. But whether you're really testing a causal relationship or not depends upon the research design. You need to design your research carefully in order to make sure that what we're testing is in fact a causal relationship and not just a correlation or a spurious relationship. The most common thing you're going to come across in reading journal articles is some variant in what's called linear regression. And we're not going to get into any math here, but I'm going to walk you through the basic logic of linear regression. And it should be pretty familiar to you actually because it's rooted in a basic linear function. In a basic linear function, you have an independent variable x and a dependent variable y. Okay? Y is the dependent variable. That's the thing we're trying to explain. it depends on the other things, right? It depends on the value of x. X is independent, y is dependent on x, okay? So y is the thing we're trying to explain, the effect. X is the hypothesized cause, right? So if we look at a line, we are familiar with this basic linear function, y equals ax plus b, where a equals the slope of the line and b represents the y-intercept. The value of the slope then tells us about the relationship between x and y. If a is positive, that means that as x increases, y increases. If a is negative, that means as x increases, y decreases. Now, in a geometry class you might have taken, you may have actually extended this out to 3 dimensions, right? So imagine a corner of a wall where it meets the floor, right? Your y-axis goes up and down, and then one side of the floor coming out from that corner would be your x-axis. The other side of the floor coming out from that corner would be your z-axis, right? So now you've got 2 slopes. You've got A and B. And we can change the value of one of those without changing the value of the other, right? So for example, you can, in that function, you can not change z, but you can change the value of x. And you can see how changing the value of x will affect y, right? Well, we can't really wrap our heads around this visually, but mathematically, you can actually extend this out indefinitely to lots and lots and lots of dimensions. And so the logic of it is the same. You hold, for whatever variable you're interested in, you hold all the others constant. You change the value of the variable you're interested in, and you see how it affects your dependent variable. And this is called multiple regression, and it's very widely used in the sciences, particularly in the social sciences. The value of the slope for each variable is called a coefficient, and it typically gets produced in a table, which I'll show you on the next slide. That coefficient describes the relationship between that particular independent variable and the dependent variable once you have controlled for or held constant all the other independent variables. So you see here a table of regression results. This is actually from an article that I published with a former student of mine, where we looked at the results of the 2010 Iowa Supreme Court retention election. In the leftmost column, we have our variables. We have the constant, that's the y-intercept, okay? Then we have the variables we're interested in. The dependent variable is the average county level vote that the incumbents won in the 2010 election. So there were 3 justices up for re-election, up for retention in that election. We took the average vote at the county level that those justices received. That's our dependent variable. So we're trying to explain county level support for the justices in 2010. And we have 5 independent variables in our analysis. The percentage of all voters in the county who are registered as Republicans, the number of evangelical adherents in the county, people who report going to evangelical churches, the median age of the county, the number of advertisements that were run against the judges, and the education level in the county. The column labeled coefficient represents the slope that gives us the relationship between that individual variable and the support for the justices. So if we look at Republican registration, see that there's a negative slope there, so that as Republican registration increases in the county, the vote share of the justices goes down. So for each point, each percentage point that Republicans, the Republican registration increases, the vote share of the justices go down by about 0.4%. And you can go right down that column and you can look at the different slopes for each of those, right? So If we look at ad airings, for every 1,000 ads, the support for the justices would go down by about 0.1%, and so on and so on. So that's how we interpret the slopes. Now, the next column is called the standard error. That's basically a measure of variance around the slope. It represents how uncertain we are about that slope. And then this column is a test statistic that we won't really talk about, but using that test statistic, we find out what the p-value is, how likely it is that we're wrong about this relationship. So we see that the p-value of Republican registration is very small, less than 0.05. Same with evangelical adherence, same with ad airings and education. So median age, though, the p-value is 0.5. That is a lot greater than 0.05, and therefore we cannot reject the null hypothesis here. It might be the case that age within a given county has no effect on the support for the justices in that county. For all the other variables, we fail to reject the null hypothesis, and we say that it's highly unlikely that there is no relationship there. And so we do think that the more highly educated a county, the more support there was for the justices. The more ads were run, the less support there was for the justices. The more evangelicals, the less support for the justices. The more Republicans, the less support for the justices. So looking at that p-value column is very important. Here we have a table of regression results from a 2015 article about women participating in violent political organizations. And we can see, just glancing at it, that it's a more complicated model than the model I just showed you. Now, in the model I just showed you, it was linear regression, which meant that interpreting those slopes is pretty straightforward. But a lot of models are not linear. We don't always think that things are going to be related in a linear way. Sometimes we might have a dependent variable that is based on probability. So in this case, for example, our dependent variable is equal to either 0 or 1. Either you participate in a violent political organization or you don't. And so the dependent variable actually turns into basically a probability that you are a 1, a probability that a woman in the data set participated in a violent political organization. And that turns out to be not a linear relationship. And so in models like this, we cannot necessarily know what that slope means, but the signs we can still interpret. Here we see that the p-values are represented in this third line of each cell. So the first line is the coefficient, the second line is the standard error, the third line is the p-value. And so what we can do is look at the slope, and we can, even if we don't know exactly what the effect is or how big it is, we know that the effect of terrorism on likelihood of participating in violent political organizations is a positive one. Women are more likely or less likely to participate if it's a small organization, and so on and so on. And all of this would make more sense, obviously, if you'd actually read the article. Now, because interpreting these regression results are not always straightforward, more and more in political science, we're representing the results graphically so that it's easier to interpret. And this represents a table, or rather a figure, that shows you the marginal effects of each variable on the likelihood of women participating in a violent political organization. The dotted line here means 0. That would be there's no effect of that variable on the likelihood of a woman participating. Each dot shows us what the effect of that coefficient would be. Basically, where is that slope in terms of its effect on the likelihood of participating. And then the long bars represent what we call the confidence interval. It's basically the error around our measure. And so when we look at a figure like this, what we're looking for is a variable where the confidence interval does not overlap with 0. Because if it doesn't overlap with 0, then we can say with relatively little error that it is distinct from 0, and therefore we can reject the null hypothesis, and we think there is a relationship there. Okay, so the size of the group makes participation less likely. If it's a small group, participation is less likely. See that that's distinct from 0. If it's a terrorist group, women's participation is more likely. Again, it's distinct from 0. The gender ideology, forced recruitment, self-determination, these are all significantly different from 0. All the other variables, the confidence intervals overlap with 0. And so we can't conclude with any acceptable amount of certainty that there is actually a relationship between those variables and the likelihood of women participating in violent groups. Here's another example. This is from an interesting paper that was published a couple of years ago that did a series of experiments with people, basically trust experiments to see how people feel about each other and how much they trust one another, depending upon whether they are a member of the other party. And so this illustrates how well people feel about one another, about their own party members, given where they are. So for example, we get, I think this is measuring affect or sort of positive feelings toward Republicans. And so we see that Republicans report positive, very high positive affect or positive feelings toward Republicans. Democrats report high negative feelings about Republicans. From that same paper then, what the authors of this paper did, it's a very interesting paper, what they did is they had people play a series of games, betting games or trust games, where you have to cooperate with people, and then they looked at people's likelihood of cooperating with one another depending upon what they knew about one another. And so what they see here is that if you are cooperating, if you're playing this game called a dictator game with a co-partisan, someone who is the same party as you, you're basically willing to give that person more money than if you're playing with someone who is from the other party. And partisanship had nothing to do with the game, by the way. It's just a question of trust. And the fact that these error bars don't overlap shows us that those groups were significantly different from one another. And notice that the bottom row is the control group, where the group was not given a party ID. And notice that both co-partisan and opposing partisan groups are significantly different than the control group. Similarly, we can look at another game they did, a trust game, again, where you're allocating money to the other player. And once again, we see that co-partisans allocated more money to the other player than opposing partisans did. Now here, co-partisans overlap with the control group, so we can't say that there's any difference between the co-partisans and the control group, but we do see that opposing partisans are significantly different than the control group. Opposing partisans gave significantly less money than the control group, and we think it's highly unlikely that those differences are due to chance. We think it's based on the fact that they learned information about the fact that the person they're playing with was from the other party, and therefore they trusted them less. So this is just another way to present results. I like presenting results this way. I do it increasingly. It's really nice for readers because it gives more meaningful interpretation of the results, and you can glance at them and see the effect of the results much better. Here's one other way we might see graphical results represented. Um, Here it's the same basic idea, but we're representing it with a linear plot. So here, this comes from a paper um, on segregation, inequality, and public good, basically looking at levels of segregation and um, the amount of resources that get dispersed to populations. Each one of these graphs actually represents the y-axis on each of one of these graphs represents a different dependent variable. You're looking at the effect of segregation on government spending on different things: roads, police, parks, sewers, welfare, and I'm not sure what that last one is. Something about taxation. And so what you see here is that as segregation increases, spending decreases in across the board in all of these areas. And what's more, the lines represent basically the average, and then the gray areas represent the confidence interval. Think of this as the akin to the bars on the charts you were just looking at. So if these gray areas were to go below 0 on the x-axis, or rather on the y-axis, that would start to suggest that there is no effect on spending. But in this case, none of them do. All right, and so we're pretty confident that these have meaningful effects on spending. Okay, so those are just a few ways. This is basic logic. We will practice these things in class. I don't expect you to be experts on this, but I do hope that by the end of the semester you're comfortable reading some of these things. And this video is always here for you to refer back to and get a good refresher on.